Okay, so welcome everybody to this next seminar within the GReTA series of talks. It is a pleasure for me to introduce Chris Brown, who will give it the talk today. Chris had a PhD in chemical engineering at Stanford University, as far as I understood, Chris, and then he joined the Topos Institute in Berkeley. And his interests are around the graphical structure based on category theory for representing interesting concept in for mathematics in general and computer science and rewriting theory more specifically. And I think both from the theoretical and for the practical implementation perspective. The talk of today is extremely relevant for our community. He will speak about agent-based modeling via graph rewriting. Chris, I leave the floor to you. Thank you very much.
All right. Thank you so much. So I want to talk about three things. I want to introduce algebraic rewriting, a library for those who aren't familiar with it. I then want to talk about agent-based programming, which is a term I'll introduce, and then talk about agent-based modeling. And the ultimate goal here is to produce a modeling framework that we can hand off to domain experts in many different types of domains, and that they themselves should compare it to the status quo and see that it makes their lives easier for comparing their models, for combining models from smaller models, editing their models and visualizing them. So let me show you what the status quo that they'll be comparing to. So there's this important class of models called agent-based models, and they have types of agents and they interact in various ways, and there's not much more you can say in general about them. And part of the goal of this talk is to introduce some formalized idea that I claim captures a lot of this existing practice without having to throw your hands up in defeat and say, well, an agent-based model is just a program that has things that we call agents in it. And so on the slide, I have three examples that will motivate me. And the problem is, how do we represent these models that you see on the screen, if not as their source code that implements them? But unfortunately, the status quo is just simply no matter what your high-level understanding is, the only formal artifact is that piece of code. And code is notoriously difficult to compare, combine, edit, and visualize. So I want to just show in more detail the code for this wolf-sheep model that you saw. It's written in NetLogo, which is a language built for the purpose of agent-based modeling. And I'll break down these excerpts of the file into three parts. First, I want to call a schema, because this is going to declare what data structures make up the state of the simulation. So NetLogo has this notion of a turtle, which is something that can move around. And this is saying sheep and wolves are subtypes of turtle, but they also have this attribute energy. And the spaces on the ground, the patches that they move on, also have this attribute called countdown. So this is basically telling you, what do I need to know to just have an instance of the state of the world? I need to tell you all the sheeps, all the wolves, all of their energies, and also what this countdown value is for all of the patches of grass. This countdown is basically capturing how long does it take for the grass to grow back. Next, we have dynamics, and these are saying, what are the possible transformations that can happen to the state of the world? So one thing that can happen is that wolves can eat sheep. And this is now a piece of code that gets executed whenever that event is triggered. So we're looking for a sheep, and then the sheep will die, and then the wolf will get some energy. And the last piece is control flow, and that's really saying, how do we orchestrate all these dynamics to happen in an actual trajectory given an initial state? And so all the sheep do this thing, and then all the wolves, they do this sequence of actions, and then all the pieces of grass, grow, increment or decrement their countdown. So this is a common structure, I would say, even among other models. So this is an explicit structure, but for example, in the COVID model, let me just go back to show you what that looked like, the COVID model in the bottom left. We also have a data structure. This is now written in agents.jl, a Julia library, where you declare a Julia structure, and that is your schema. And you write a Julia function for each dynamic, each thing that can happen. And then the control flow is saying for all pairs, they transmit disease, and then they maybe bounce off each other. So this common structure is something that I'll try and make explicit at the end of the talk. And the takeaway from this slide should just be, wow, this is really unwieldy syntax for comparison, combination, editing, visualizing. Because if you were tasked with writing a generic combiner of models, for example, you have to write a function which someone later can come to you and say, hey, what if sheep could get COVID? Make it happen. How do you do that without having to, start from scratch or really get deep into these implementation details? That would be nearly impossible to write. So I do think those 4 virtues I was going for do hold for things that are specified in more of a graph rewriting language, because we actually understand mathematically what these rewrite rules are. We understand them categorically. I don't think I need to sell graph rewriting to this community, but I do often need to make a case for it for engineers who are used to thinking in imperative or even pure functional languages. So why is this a hard sell? Well, I think it's because rewrite rules really capture atomic changes really well. But the moment you start having multiple applications, you get inherently this non-determinism from the choice of match, from the choice of rule. And just as a community, engineers and modelers need a lot more determinism when they're using rewriting rules than the graph transformation community, to my understanding. So the question is, what is a good syntax for talking about applying rewrite rules in an algorithmic way? Well, this is a nice systematic view from Raiko and David's book, and they talk about all these different control structures that you can have. And that is really good, but I think it's missing something. So let me show these general strategies for control. The sort of lowest level is that you just have a set of rules, and you try to control the control flow via constraints on your rules, as well as sort of sneaking in your program state into the graph. Like you have a little node that says, hey, I'm on step number 7. So this is not ideal. There was a cool paper that I saw that had a graphical language for talking about this control flow, where you have sort of sets of rewrite rules in these boxes. And whenever you successfully apply a rule, you exit through a yes arrow. And if you fail to apply a rule, you exit through a no arrow. And so I'm going to draw on this idea, but I think this is not enough complex control flow. And the problem I'm going to really stress on this slide is we don't have control of matches. I don't have a notion of saying, I want to use this match for this rewrite rule and this match for this other rewrite rule. It's always a matter of just a constraint. Then a more common type of thing to do is that you have some sort of programming language like syntax, where I can say, an expression tree with if and loop and when. And yet I have some primitives that are rewrite rules that execute. And so I've highlighted the rewrite rules, for example, in this progress paper, but GP2, I'll have an example of that later, and that's similar. And so one, we've lost the nice graphical nature of our syntax, which is sad for me. And then 2, we still don't really have explicit control of matches. So I'm going to, after I introduce algebraic rewriting, talk about a graphical language for control flow that still allows us to say, use this match in a certain intuitive way. So just to introduce algebraic rewriting, it's a library for graph rewriting written in Julia. It's part of this algebraic Julia ecosystem, which is a whole network of at least 50 packages that either implement computational category theory or apply it to some concrete domain. There's a lot of general computer algebra features, but there's a lot of emphasis and special support for this category of C-sets or attributed C-sets. And so that is going to be, I'm going to mostly talk about the C-set of directed multigraphs, just because that's very straightforward to visualize, but C-sets really have a lot more expressivity from some perspective. So algebraic rewriting in particular, I just want to highlight for this community the sorts of things that it can currently do, which is that we support lots of various semantics for rewriting. Because these C-sets can be attributed C-sets, or as we call them, attrits, we can then do rewriting with attributes. We have support for application conditions. So this would be positive, negative application conditions, but also nested first-order logic constraints. We have automatic homomorphism search, so that would be finding matches, for example, but also incremental homomorphism search. So when we make a small change to the world, we want to incrementally update all of our HOM sets that are sort of watching what are all the current matches. So we also have something called functorial data migration of rewrite rules. So if you write your rewrite rules for a system, let's say of graphs, but then you realize, well, I need to generalize to Petri nets. My edges actually have multiple inputs and outputs. Then there are these canonical ways that you can declaratively specify between the schema of Petri nets and the schema of graphs that will allow you to do this migration in a way that is, mathematically verified, but also automatic and actually very user-friendly. And then I'll just throw this in because I know Nick Baer is interested in computing partial overlaps between graphs, and this is also something that we're doing now. One nice thing about working in a modern language that is amenable to scripting is that installation is really easy. You can just download Julia and then say add algebraic rewriting from the general repository, and suddenly you can launch into examples in the terminal, or you could write a little script, or you could actually make your own library that's based on this. So I think it's from a usability perspective, there's a lot of advantages to working with Julia. So I actually had about 10 minutes of CatLab basics that I've moved to hidden slides at the end because I just don't think there's time. It would be great if everyone here could look at CatLab code, literal CatLab code, and understand it and see how actually intuitive and close to the natural mathematical practice it is. But I don't think I'll have that, so I've only retained the summary slide of what I taught you, which is no longer what I taught you, but you can see the sort of things that would be basics for CatLab, which are good to understand if you're looking at algebraic rewriting code, because algebraic rewriting is basically a thin layer on top of CatLab. So CatLab lets you declare these C-sets. So you can manually declare it. So in the case of graphs, that would be saying, well, this is my set of edges, this is my set of vertices, these are the source and target functions. So you could do that manually. You can do that via custom functions, for example, cycle graph for a for cycle. There's expressions, like give me the terminal object or give me the subobject classifier. Or give me the subobject classifier plus the terminal object. So we can build things via categorical constructions such as limits and colimits. We can also declare morphisms between these things. This is the other big building block. So that can also be done manually, where you're specifying, for example, the vertex component and the edge component. But more often, we can just say this domain and codomain and just give some constraints, such as that it's monic, or maybe it's monic on vertices, and we initially send edge 1 to edge 7. So that's a very powerful language that you can usually pretty succinctly express which morphism you want. I would then have shown you all these different C-set schemas, for example, discrete dynamical systems, graphs, Petri nets, and then for attributed C-sets, maybe something more realistic, like a chemical reaction network where we have stoichiometries that are real numbers and atomic numbers, which are integers, but with this sort of external meaning, not just like the integers here, which are meaningless identifiers. And then lastly, data migration. So being able to convert, these things in between each other in canonical ways. So I'm not, unless there's time at the end and people are curious, I won't go through that, but this is really the building blocks upon which algebraic rewriting sits. I do have some code here. The focus of this talk won't be the actual code that implements things, it'll be the concepts. So, but just to give a taste of code, this would be declaring a rule where we say, first, we'll give semantics. So maybe, by default DPO, but here we're going to say a single pushout rule. We give the span in terms of the left morphism and the right morphism. So this is going to essentially delete an edge by giving a map from 0 to the edge, and then identity of 0 on the right-hand side. We can add some constraints to the rule, for example, saying that its matches must be monic and that it must have these positive and negative application conditions. So you have a language, and now we have this del edge object, which we can then do things with. For example, we might take some graph and apply the rewrite rule to it. We might pick a specific match. This is using that homomorphism search to just grab a particular edge from G. And then we might say rewrite this rule using this particular match. And we can also say rewrite match maps, which is going to essentially give you the whole derivation diagram that comes out, not just the resulting graph. And I'll have also a little example of attributed C-sets where we're going to actually match a pair. Now we're working in the category of weighted graphs, and we're going to match two parallel weighted edges, throw away their edges, but then replace it with one edge that has their product. So here we're actually allowing ourselves to use arbitrary custom code to do some business logic with the values that got matched, let's say, from our pattern. So this should be done with caution, of course, because to the extent you're injecting custom code into your rewrite rules, then it makes a lot of the math no longer nice, such as, functorial data migration. It's not going to operate on this code expression easily. So that is a good breakpoint. I'm happy if people want to ask questions during, but I will then talk about actually now this syntax for rewrite and control of matches and control flow. But if there's any questions about CATLab, algebraic rewriting, I'm happy to take any at this point.
Let me take the opportunity to remind the present people that they can also ask questions on the chat, in which case I will check if the question needs an immediate answer or can be postponed to the end of the talk. Okay, so this was not a question, sorry, Chris, but okay, I think you can go ahead.
Sure. Okay. Yeah, sorry, my screen is configured such that I can't see the chat, unfortunately. So thank you if you jump in. Okay, great. So I want to now try to tackle this main problem, which was how do we represent control flow and control of matches. And first, I want to talk about symmetric monoidal categories. So when you're fortunate enough to be working in a symmetric monoidal category, you're licensed to use these wiring diagrams as a syntax for talking about morphism. So this unambiguous formal semantics of how do I interpret this wiring diagram as a morphism in my category. So that's the first benefit. It's nice that actually you have this separation of syntax and semantics, because maybe I want to change my category that I'm talking about. Maybe, I want to start, I'm interpreting these morphisms as deterministic processes, but then I want to switch to probabilistic processes. Well, you don't have to change your model, your diagram at all. You can just simply change your semantics. So this is the first advantage. And yeah, if I want to explain this, I'd say like the vertical dimension is this tensor product. So this on the left hand, we say this is a morphism from A tensor B to C. And the data of this, you can sort of break this up into three slices, where the first slice is this copying A and identity on B. The second slice is identity on A and applying whatever morphism 3 is. And then the last slice is just applying 4. So you can see this sequence composition is the dot, and the vertical composition is the tensor product. So we can also use that composition in the category as a way of composing diagrams in a graphical way. So if we want to compose in parallel these two diagrams, we're simply sticking one on top of the other. And if we want to compose them in series, if they match head to tail, then we can simply just pop them side by side. So that is a really useful thing to do of building up these things compositionally. And furthermore, I'm now having loops in these. So I'll just note that if your category has further traced structure, we can make sense semantically of what these loops actually mean. And then the last, I would say, advantage or perk of working with SMCs is that we can do an operatic substitution. So this box right here has 2 inputs and 1 output. So we can make sense of what it means to substitute in for box 1, and we get some kind of non-trivial chasing of these wires to get the resulting diagram. So this is another way of hierarchically building up a program from subroutines. So what sorts of things have this trace symmetric monoidal structure? Well, the category of sets and partial functions do. And we're going to use coproducts as our tensor operation. And that means we can use that graphical language to talk about functions, partial functions. So I'm going to start talking about rewrite rules now. So let's think of the rewrite rule add loop as a function from the set of graphs, all possible graphs, to 2 copies of the sets of graphs. We're going to distinguish when we successfully apply the rewrite rule and when we fail to apply the rewrite rule. So add loop is going to match a vertex and add a loop to it. So if you gave it the empty graph, so this is the rule on the left, and now I'm having two example input-output relations on it. If you fed it the empty graph, it would be you wouldn't have a match, and so you would exit the bottom. Sometimes it's the bottom, sometimes it's the top. So I'll mark it with an X. You exit the X door with your input unchanged. But if we enter with something that does have a vertex, then we'll exit the top, and a loop has been added. Now, there's a certain irony here because I'm saying the whole point of this framework is to give control of matches, and I just pretended as if this was a deterministic function. So just trust that in a few slides, I'll talk about control of matches. But just to lay the groundwork, pretend as a fiction that this is truly a function, and there's a deterministic but arbitrary match that gets chosen when we apply this rule. So let's already put this to work. This is already enough material to show some interesting things. So if we were told we want to make a program that adds a loop to a vertex, but if no vertex exists, add a vertex and then give it a loop, well, then this program would actually meet that criteria. So we would first try to add a loop, but no vertex exists. So we then move down this branch. We'll then add a vertex and then end up back where we started. And now this rule will succeed and we'll exit. So this is we already have, while loop style control flow, and we have a very limited form of if statements. It's really the only if we can ask is, does a rule match? So let's try to...
Sorry, Chris, are you implicitly assuming add vertex cannot fail? Or
so no, this diagram doesn't assume that. It's simply saying, regardless of whether it succeeds or fails, you're going to merge those two control flow paths and do the same thing no matter what. It happens to be the case that add vertex can't fail. Yeah.
Okay. Thanks.
Yeah, if I wanted to denote that, like asserting that it's not possible for add vertex to fail, which is true, I might put a block. Maybe I wouldn't have an out port for this X thing right here. I wouldn't have a wire coming out of the X. But there will be no such examples of that in this talk. Great. So I'm saying now we want to have some kind of if statements, but more general than just merely does a rule match or not. So that means I think we need to introduce a new primitive. And so these boxes, remember, we're working in sets. So sets and partial functions. So in principle, any box could just have an arbitrary function, but we don't want to reason about arbitrary functions. So we're going to have a curated core of primitives that are expressive enough to do what we want, but easy to reason about. So this new primitive is going to be very restricted. It's going to redirect its input from the input to one of its output wires. It can't modify the input at all, so that's what this condition is. So really think of it as just a function from A to 1 through n, where n is the number of output wires. So what can we do with this? So one thing we could do is we could have a function that takes in a graph. If it's a DAG, we're done. If it's not a DAG, we're going to remove a deterministic but arbitrary edge, and then we're going to go try again, and eventually this will succeed, and we'll get a DAG that comes out of this. Alternatively, we could feed in a graph and remove some edge, and removing that edge, let's say it's including the source and target, there's a chance that results in an empty graph. And maybe we want to distinguish for our future decision-making whether or not we have an empty graph or not. So here, if we post-compose this rule with the isEmpty control flow predicate, then we'll have two output possibilities that we might want to distinguish later. So these control flow boxes allow us to separate what's controlling things versus what's actually changing the world. And now we have if and else and while, but we don't have for loops because these boxes don't have any internal state. They don't have any way of encoding a history dependence. So the first generalization to what I've shown you, this category of set star, will be to allow this. But I'm hoping that up to this point that we can sort of make sense of, little programs like this. It might be hard to wrap your head around if it's really big, but if there's just two boxes, I'm hoping these diagrams are intelligible. Okay. So the first generalization I want to make is something called a Mealy machine. So a Mealy machine or a dynamic function is like a function, but it has its own set. It's and there's an initial state too. And when you apply the function, it can change that parameter. So it's a dynamic function because it's like a function that you run, but every time you run it, it can change its internal state and therefore alter its future behavior. And so what we're going to do is we're going to allow these control boxes from the previous slide to have a non-trivial state if we want. So for example, a control flow box that implements a for loop, so to speak, might have an internal state that's a natural number with some initial value, let's say 3. And every single time you go through it, it decrements that value. And so the first 3 times you run this function, it will exit through the top wire, and subsequently it'll exit through the bottom wire. So this function right here actually doesn't depend on A at all. It really just depends on S. So what's an example application of this? Well, maybe you're tasked with making a program that someone's going to plug in somewhere else, but the specification is it needs to behave like add loop the first 3 times you use it, and subsequently needs to behave like delete vertex. So if we imagine passing a graph into this implementation on the right, the first time we pass in a graph, it's going to go through this for loop and exit through the top. And then the behavior of the overall box will simply be the behavior of add loop. It's as if delete vertex didn't exist. And so the first 3 times you do that, it will look, phenomenologically like add loop. Then afterwards, every single time you run through it, it will look as if it were just delete vertex. So this is one way of putting this for loop to work. And so now I would say we have a pretty robust language for control flow. I haven't yet said anything about addressing control of matches, so now I want to talk about that. But if there's any questions at this point before I add one final complication. Oh, sorry, I see my footnote now. So yeah, it's true that Mealy machines actually don't form a symmetric monoidal category, and it takes some high-powered category theory to actually show why morally we're entitled to think of them as if they do. In reality, they're presentations of an object of these behavior trees, which actually do form such a category, but it's more user-friendly and intuitive to think about Mealy machines. So I'm going to just really stick at the Mealy machine level and leave the details to the paper. And yeah, so that just keeps things nice and simple, that we think of, yeah, our primitive boxes really are just functions that potentially have internal state. Okay, so I'm going to now complicate things ever so slightly in order to talk about control of matches. So this is where the notion of agent comes in, but I think focus is equivalently a good word. So every wire is now typed with a particular graph, for example, which is the shape of the focus or the shape of the agent. And the values sort of that flow along these wires are no longer graphs, but they are graphs with a distinguished, A or a distinguished B, where distinguished means I have a morphism from A into G, where we have some state of the world G. So this is a little bit of extra data now that's flowing on these wires. And that means that a rule needs to know what sort of distinguished object is coming in, and it needs to know what kind of distinguished object is coming out if the rule is successfully applied. So for example, consider A equals B equals just a vertex, and we're talking about add loop. So now add loop is not expecting a graph, it's expecting a graph with a distinguished vertex. And it also needs to output a graph with a distinguished vertex. And so in general, we need more information now to specify this rule. So the data actually is not just our span that we had before, but it's actually a span with a map in from the input shape, and then map in from the output shape into the replacement. And this is, how does this actually work? Well, we receive as our input this map from A in to G in, and this map from A in to L is implicitly setting up a commutative diagram constraint. We're basically saying the only valid matches are ones that make this diagram commute. And that's a really powerful technique, mainly because I think it allows us to have a really flexible gradient between 2 extremes. Because if the input shape is simply the empty object, then this commutative diagram imposes no constraints at all. But if that A in equals L, then it's complete determinism. We have exactly, at most one match we could possibly apply. So, and we can do anything in between. And I want to say that semantically, this means, adding this extra data is the difference between a rule that says add a loop to some vertex to adding a loop to this vertex. This data here up top is what allows us to have rules which make reference to demonstratives like this vertex. And for the output agent, well, we do the normal rewrite rule and we obtain this map from R to G, and then we simply compose these two morphisms in order to get our output agent. And that's how we end up getting a distinguished B coming out if we successfully rewrite. So I'm now going to do some examples that put this all to work. So the first example might be just two rules that are going in series. And so if we look at the second rule involved, there's a difference between the input and the output agent. So this is taking a particular source and target vertex. We match whether or not there is an edge between them. And if there is an edge between them, we try to delete the target and the edge itself. And then our output is simply a single distinguished vertex. Likewise, merge vertices naturally has an interface of two vertices as its input, because we're saying merge these two specific vertices. And its output interface will also be two vertices, but it will just happen to be the case that they will end up referring to the same vertex whenever you apply the rule successfully. So an example run might be this input graph where we come in with these two vertices distinguished, highlighted in red, and then we apply the merge rule. It's successful, and so we end up with this graph. But then we try to remove target and edge looking at this vertex in particular. So we're looking for a loop basically on this vertex, but there is no such loop. So we actually exit out through the bottom, the X door of this second rule with the graph unchanged. So this is our first example of how these focuses or these agents are actually controlling how we apply the rewrite rules. I wanted maybe a less toy example, so I saw this example of classifying binary directed acyclic graphs. And so this is an example from a GP2 paper where given this rewrite system and this rewriting program written in GP2, basically you will succeed if it is a binary DAG and it will fail if it's not a binary DAG. And this was actually in an earlier GReTA talk, and it took a good 10 minutes to explain in full detail, so I actually won't do that myself. The point is there is a rewriting program, there's a bunch of rewrite rules, and this is something that you can do. Some high-level points I want to establish is that GP2 has special support for rooted graphs, and that's in order to make computations like this easy and to specify and efficient. But the viewpoint, from our viewpoint, this notion of like a rooted vertex is really just a special case of a focus, an agent shape, where it is just a single vertex. So there doesn't need to be any sort of special support for this, but this just comes along for free. Also, in addition to rooted vertices, there's also a notion of a flag, which is meant to sort of inject some control flow into the state of the graph. And from the example that I'll show, this won't be necessary. So this is going to be a rewrite in a category not of directed multigraphs, but also directed multigraphs with distinguished edges, which are going to basically the edges that we've seen before. And the whole program actually just looks like this. So the isDAG program comes in. It has this initial rule, so now I'll show the rules too. This will be too involved to actually go into full detail, so I'm more flashing it on the screen. You could sort of pause on YouTube maybe, or we could come back to it at the end. But the sort of brief run through it is that there's a rule init which sort of picks a vertex. It's really picking a connected component via some particular vertex. If there are no connected components left, you exit through this X route and you're done. And if you exit the overall program through this top door, that means that it is a DAG. But we take a connected component, we then do this top procedure, which is basically trying to move our distinguished vertex to the top of this connected component. And if that could fail, in which case perhaps we get in a cycle, so then we would exit through the fail door. But if we get to the top, then we start trying to eat away that whole connected component via this del subroutine, and that could also fail. So those are two ways you could fail. But if we fully eat away and delete this entire connected component, then we'll exit successfully and then go back to process another one. And so you can express, again, top and del as these very relatively simple compositions of just rewrite rules. And I've got all the data here, but I think going through each of these rules and why this is a correct analog of the program that I showed here is maybe not the best use of our time. So maybe we'll come back to it. But this is just to show that there is a quite, applied, useful non-toy example that already the tools that I've shown you can accomplish. So there's further expressivity that we might want, which is how do we fluidly and ergonomically switch from agent to agent, let's say. Because applying a rewrite rule is one way to switch agents, but we wouldn't want that to be our only way of switching agents. So now I'm introducing a weaken primitive, which is given a morphism from A to B, that is a tool itself for converting B agents to A agents without changing the state of the world. And so, for example, this is a morphism that sends a vertex to the source of an edge, and that's going to allow us to convert edge agents into vertex agents. So let's say we come in with this particular edge distinguished. Well, that is a morphism from the edge into the underlying graph. So if we precompose with this morphism, we're going to get a distinguished vertex, which will be the source of that edge. And you can think of this as equivalent to, we could implement weaken with a rewrite rule where the input agent and LIR are all equal to the input agent. So the graph is not going to change at all. And then we simply precompose with B. It's nice to think of it as just a different primitive, but in principle, it is equivalent to that. And I'll note that you can always weaken with the initial object. So this is essentially, there's always this morphism from the empty graph into whatever your agent shape is. And so therefore, we always have the ability to just throw away whatever we're focusing on. So this is just like a useful operator to have special. So that is going from an agent to, I would say, a less specific agent. Now, how do we get to more specific agents? Well, that is this thing called a query block. So we can give it semantics via describing what the Mealy machine is that a query block is. So a query block, the internal state is going to be a bunch of homomorphisms. When you come in with a particular A agent, it's going to then query all the possible Bs that are related to A in a certain way, and it's going to store all of them in its internal state. And then every single time you do this loop and you do a subroutine and you come in through this other wire, you're going to then pop off a new B that you've stored and then do the subroutine with that particular B. So it's kind of like a for loop, but it's looping over agents that are related to A in some way. And so the simplest way we could talk about a related A and B is just via some sort of span with some overlap between A and B. And so what we're implicitly doing when we enter the box for the first time is to query all of the homomorphisms from B into our state of the world that make this diagram commute. So an example might be we come in with a distinguished loop, and we want to get all pairs of outgoing edges from that loop that are from that particular loop. And so the overlap is equal to the input pattern, and we simply have this extension right here. So let's see an example of this in action. The task is fully connect all of these outneighbor vertices of some distinguished loop. So I have this exact span living inside of this yellow Q block. And so when we enter in, we're going to have a pair of distinguished outgoing vertices. We're going to just throw away the loop focus so that we just have a pair of distinguished vertices. We'll add an edge between them and then throw away our focus and re-enter. So let's actually see, walk through quite slowly what this control flow is. So I'm going to enter in with a distinguished loop. So for example, this loop right here. The first step when I go through the query block is to switch my focus from A to B, and I just get one of the Bs in some order. So I'm distinguishing, there's one, vertex 1 and vertex 2 of this pattern. So let's say vertex 2 is the top one. So the next step is going through this weaken box, which is saying ignore the loop in the outgoing edges. So we now have thrown away that from our focus. Now we have the right interface to plug into add edge, which requires a distinguished pair of vertices. And add edge is going to add a vertex, add an edge between those two vertices. So that's what this third box is right here. And then we go through this forget everything box. And so we end up with the underlying graph, but no distinguished anythings. Now we re-enter the query box. And remember, the semantics of the query box is you're going to do the subroutine for every such B that met this initial criteria. So then we pop off, we've thrown away the first, there's only two matches of this, this set only has two HOMs. So we've just processed the first HOM, and now we're going to process the second HOM. So it involves the same two vertices, but now vertex 2 is the bottom vertex. Again, we throw away the information about our distinguished loop, and now we're just focusing on two vertices, where the 2 is the bottom one. Add edge is going to then add an edge in the opposite direction, and then we again go through this exclamation point, and now we're back into the query block. But now we've finished processing all of the sub-agents, you might say, all of the Bs. And so now we can exit again with our original agent here. So this whole program right here was a means of looking at a distinguished loop and fully connecting all of the outgoing vertices. So that's going to be it for examples of this. There's definitely more complicated things we can do, but the primitives now that we have to work with are these rewrite rules. We have control flow, which is purely for control flow. We have query, which gives us more specific agents, and we have weaken that gives us less specific agents. And this is, I would say, a really powerful language that does meet all the criteria I was going for. And so, for example, we can actually implement this wolf-sheep model with a diagram just like this. And I used to call these agent-based models, but over the course of the past year, I've learned to think of them as agent-based programs, not agent-based models, even though I can implement a model such as this wolf-sheep simulation. So I'm not going to go into the details of this model, but the idea is it's something that we can express. So why are these programs and not models? Because they certainly feel less like programs than this kind of syntax, which is equivalent. Like you could compile these wiring diagrams to a syntax like this that is looking for morphisms, and if a rule is successful, you do this, else you do that. So it feels not like a program because it's graphical. You've got this graphical composition and substitution, and we can much more easily change the overall semantics than you could if you wrote a piece of code, which sort of fixes a semantics ahead of time. But nevertheless, I want to say this is not really modeling, because the control flow is fundamentally imperative rather than declarative. So if I want to understand some part of a diagram, you really need to be running a simulation in your head. Furthermore, there's no built-in notion of time. This is the more difficult thing. So it's always this linear sequence of events. There's no notion of concurrency, and there's no notion of continuous time. So these are what's going to be addressed in this the last section. So I want to say this is work really hot off the presses this past month with John Baez, Nate Osgood, and Xiaoyan Li who are computational epidemiologists at University of Saskatchewan, Evan Patterson also at the Topos Institute, and Sean Wu at Merck. So this is meant to come up with a formalism that captures truly agent-based modeling rather than just agent-based programming. And so I'm going to now refer back to my three-part recipe for an agent-based model now made explicit. So first, we need a schema. And you might be able to guess that our perspective on what a schema is going to be literally a schema for a database or an attributed C-set schema. And that is a way of saying what data is required to specify the state of the world. So, for each of these objects, there is a set associated with it. For each of these arrows, there is a function. And then there's some details about how attributes, what the semantics of that are. So next, so I'll say we want to talk about continuous time, but discrete events, in addition to continuous dynamics that I won't talk much about. So we want continuous time, but discrete events, where the discrete events are rewrite rules. So our required data is a collection of rewrite rules. that have associated timers. And I'll talk about in the next slide what these timers are, but they're basically controlling when do the events happen. So the rewrite rule then is the dynamics, and the timer is the control flow. But now it's a very declarative control flow as opposed to an imperative one. I'll also note that, at the end of the day, the users might not want to directly work with rewrite rules. They might want to work with a more friendly syntax that will get compiled to rewrite rules. So here is a Petri net where we want to interpret this as two different rewrite rules. If we're working in this schema, we might say, well, the infection transition really corresponds to this rewrite rule, which says, if you have a susceptible and infected person living on the same vertex, that will delete the susceptible token and replace it with an infected token. So let me talk more about so the rewrite rules are really this lingua franca that sort of live at the core level, but there might be various ways of presenting rewrite rules that a domain expert might prefer in their own native diagrammatic reasoning. So these are really capturing, these timers are capturing semi-Markov processes. And the semantics are basically that we're trying to talk about probabilistically what the residence time is of a certain pattern. So we get a pattern match for a rule, and suddenly a timer, we draw randomly on some distribution, how long is it going to take for this rule to actually fire? And that's going to be conditional on nothing else happening that removes it from that state that allows the rule to fire in the first place. And so staying in this, this residence time of staying in this state is really the idea of a match persisting over time. So let's look at an example. If my initial state of the world is one susceptible person and two infected people, so implicitly here, susceptible is green, infected is blue, and recovered is yellow. So at T0, there's 4 possible rules that can happen in an SIR model. Every infected person could recover, and so that's going to be characterized with just like an event where there's just a single number that's going to say that person recovers. But there's also infection, 2 possible infection events, and I'm going to represent infection events as just like these tuples of who's infecting whom. So just from this initial state of 1 susceptible and 2 infected people, there's 4 rules. There's 2 possible recovery events, and there's 2 possible infection events. And so given these distributions, we randomly draw what the time of firing is for those 4 events. So that all happens before the simulation even starts. And so the actual process of the simulation is then advancing this clock forward in time to the next possible event. So let's say we then, this is the initial state. Well, then the next thing that happens is we jump to TA, and we fire this rule, which is that person 2 recovers. So you can see person 2 has recovered, but in virtue of person 2 recovering, we have now invalidated the person 2 infects person 1 transition. And so this timer actually then is invalidated, and we can check that with basically commutative diagrams, and there's a rigorous way of saying whether or not this match actually still exists. So that means actually the next time step is actually jumping over time B and jumps straight to time C, which is that person 1 is infected by person 3. So now we can see the state of the world. But when that happens, actually a new match springs into existence because now person 1 can recover possibly. So we randomly sample at that moment in time and see, oh, actually there's a new time, TE. And it happens to happen before TD. So the next thing that happens is we jump to time E, and person 1 recovers, and then the next thing that would happen would be person 3 recovers. So this is this notion, this is really a good example of continuous time, but discrete events. And so this is nice that we're not running this sort of like every little time step, we're sort of incrementally updating things, but we can actually have long jumps if nothing is happening over a particular time. And so the generalization of this is that it's not that for every rule we just have this particular timer probability measure, but we actually could have that depend on the state of the world at the time of the match. So perhaps, this curve is going to depend on the viral load of the infected person. Or maybe the probability of recovering is the global property of the total number of doctors in the simulation. So there's a lot of flexibility then on how your language for talking about how likely these events are going to happen. So that's a richness in declarative control flow. I'm not going to focus on this, but there's also a way of incorporating continuous dynamics on this. So maybe these antibody and viral load attributes are actually updating in a sort of continuous way. And that is not really captured well. So yeah, rewrite rules really capture combinatorial changes and discrete changes, but this continuous changing is also important in agent-based modeling. So we want to have some story for how that gets incorporated. So one way to do that is to have a pattern instance. So this would be two infected people on the same vertex, and they have sort of variable viral load and antibody counts. We can give an ODE for that particular pattern, and then for every single match, so at T whatever, oh, sorry, I'm seeing my screen has now had some issue. Let me stop sharing and share again. I'm not sure what just happened. Okay. Hopefully we're good now. Yeah, so for every single pattern match, so for every single homomorphism from our pattern into our state of the world, we sort of get a copy of these dynamics that get added in. And so if that's not clear, it's okay, because the focus of this talk is really about the rewrite rule integration. Oh, no, again, I'm seeing Adam Solomon pop up. Like, I can't see my...
Sorry, by accident. It was an accident. Sorry about that.
Yeah, no worries. I'm going to stop sharing and share again. Okay. So let me show some examples of this with my remaining time. So one interesting thing from the fact that our probability distributions can be, or measures can have Dirac delta distributions, is that you could have simultaneous events. And that was something that was not possible with the agent-based rewriting, or sorry, the agent-based programming. So we can actually simulate the game of life in a very declarative way. So the whole code basically fits on this slide other than one helper function. So let me actually walk through this step by step now. We need to declare a schema. And so in CatLab, we can do that with this present macro. And we're saying we're going to extend the schema of symmetric graphs to add a new object called life and a new morphism called live, which is basically a distinguished set of living cells and a map which pick out which vertices are these living cells. So that is our schema. We then have a data type talking about functors from schema life graph into set. So basically this is the set of C sets.
Sorry, just one question. Is this coding about gaming?
Can you repeat? I hear static, yeah. One more time, Adam.
Is this game about gaming?
This game is the game of life. So Conway's game of life. Yeah, if you Wikipedia that, you'll see. So the idea is that there's a bunch of cells that are connected to each other, and every time step, there's a simple rule that decides whether a cell lives or dies. If you have 2 or 3 neighbors, you can stay alive. Otherwise, you die. And if you're dead, you come back to life if you have exactly 3 neighbors. So that's just called an automaton. And we can actually implement that. It's kind of a notion of an agent-based model, and we can implement it using the framework I just told you about. So up top, we've declared our schema for the game of life. It's just a graph, a symmetric graph that has a distinguished subset of vertices, basically the living cells. Then there's a couple helper building blocks. So the first one is just called cell. And that is just the isolated vertex. It's not necessarily alive, it's not necessarily dead, it's just a vertex. The next thing is a live cell. So this is saying I have a vertex and moreover, it's alive. And then there's a unique homomorphism from the cell, just the arbitrary cell, into the live cell. So that's one key building block. And the other building block is something called living neighbors. So if I called living neighbors 3, that would basically give me a live cell map into a live cell that's surrounded by 3 living neighbors. And optionally, I could say alive equals false, in which case this is not alive, and the cell over here would not be alive. So that's really all we need then to declare all of our rules in a very simple way. And I'm just going to show the underpopulation rule, which says that a cell dies if it's alive and it has fewer than 2 neighbors. So this is simply a rewrite rule where the left-hand side is the pattern is a living cell. The right-hand side is a cell that is not living. So this, applying the rewrite rule will basically say, well, remove the life from that cell. And then to make it match only for cells that should die from underpopulation, we can simply say, well, living neighbors 2 is a negative application condition. So living neighbors 2 will be this morphism from L to N. And you can see if we try to match, let's say, one of these corner living cells, that the negative application condition will not trigger because there's only one living neighbor. But if we tried to make this middle cell die from underpopulation, the negative application condition would kick in and we would not be able to apply the rule. Likewise, we can talk about overpopulation condition, and then for that you spring into life when you have exactly 3 neighbors. We can do that with a combination positive and negative application condition. And furthermore, if we want that rule to only apply to dead cells, not merely cells, then we can add a negative application condition which says, by the way, you can't apply this rule if the cell is already alive. And that's it. We have our model. Our model is simply these 3 rules with their associated timers. So this tick rule construction is making a rule and also giving us a timer, which is a Dirac delta on 1 time unit. So we can simulate the game of life in this way. And then all the events happen simultaneously. And we can do a check at runtime to see whether or not the simultaneous events conflict with each other. And it would be either an error or maybe the user wants it to be some arbitrary order for breaking ties if they want. The next example is I'm showing, again, this idea that we can have a user-friendly presentation that gets compiled to rewrite rules under the hood. So here we're declaring the SIR Petri net. So this is what it looks like. We're saying susceptible infected people turn into 2 infected people, and the infected people can recover. So the idea is that that is sufficient to both specify a schema as well as the rewrite rules. And the only thing missing from this Petri net really is the timers associated with it. So we could put a Markov timer, and we could also put a non-Markovian timer, let's say, for recovery. So it's simple that we can just create an initial state and then run the agent-based model on the initial state, and we get a plot out like this. So this was really, really simple. There's some stuff about making this efficient that I don't think I have time for, or I can talk about if I have time. Basically, in certain fortunate cases, you don't actually need to maintain explicit matches, like have a time for every single possible match, for example, every pair of susceptible infected person. Rather, because there's a certain symmetry, you can simply have one timer that has its rate multiplied, and then when it comes time to fire that rule, you randomly pick a susceptible infected person. So there's a lot of certain efficiencies we can get when our, I would say, our pattern is a co-product of representables. Also important for performance is the idea that we care about our matches at every point in time. So we need to be able to incrementally update our hump sets. And so I've worked out something like this. I'm very interested to see how what I've worked out compares to the literature. And lastly, I want to say that one doesn't have to choose between an agent-based program and an agent-based model. For example, there's certain sometimes you really do want that explicit control. This already came up by working with epidemiologists, Nate and Xiaoyan, where they said, well, I want something where there's a timer, and when that timer fires, I either do a rule 1 or I do rule 2, but I don't know which one, or I try to do rule 1 and then I try to do rule 2. So really the natural generalization is that it's not that we associate a rule with a timer, but we associate an entire agent-based program with a timer. And it just turns out that rules are a very special case of that, a simple case, but you might want to do some more complicated logic when the timer fires. So that's it. In conclusion, I think algebraic rewriting is a really expressive and powerful playground for rewriting concepts. We'll say that we're moving in a direction towards removing the sort of dependence on Julia, but rather we want to have sort of a core categorical language that can then be instantiated in Python, Java, Rust, etc. So that's a direction I think we're moving. That I think will increase the sort of usability, tractability of this. I talked about graphical rewrite programs. Thank you, Adam. And I talked about agent-based models, which are more declarative in that we can actually compare these things. So with that, these are some resources, some libraries, some blog posts, some papers. This is actually missing. I have a blog post on the incremental home search updating, so I'll add that. And then some specific models for you to check out. So with that, thank you for your attention.
Thank you very much, Chris. It was really extremely interesting. I ask the audience, is there any question or remarks? Nick, please.
I mean, thanks a lot, Chris. Superb to see this update. I mean, very, very nice work. And I have a lot of questions, but maybe one quick one. Sometime in the beginning of the talk, you had this overview of what Algebraic Julia is currently doing. And because I mean, I remember we had a talk by you some long time ago already in GReTA, at least 2 years.
Yeah.
So it seems, so everything in this list, so for example, these overlaps between C-sets, can you do them under conditions, or is it for the moment without conditions? I mean, can I combine the idea of constraints, or would I have to hack that and just do it?
That might be currently a hack job, but I think something that we can talk about. Yeah. So this is this right here. Yeah. So certain things that made this much faster is searching for sub-objects now. We have an explicit construction of a sub-object classifier.
Excellent.
And doing hom search into that is actually much more efficient than any kind of other means of constructing sub-objects. So there's things like that that have made this possible, but that doesn't yet interface with the constraint machinery. But I think that to the extent that was a bottleneck, it might be made much easier. So yeah, it's just something that I haven't tried. I'd be happy to talk with you more about that.
And could you show again this slide where you explain this construction of these control? How is this called? These agent kind of boxes. So
yeah.
So the idea is that before these diagrams were roughly speaking about. I mean, a string diagram would have been something where you could have plugged any graph under no extra circumstance, and now you're essentially plugging graphs in the over category where you basically. I mean, you replace the category with the over category. So basically, you ask the data of a morphism from whatever you plug as, I think you call them agent or control or something.
Yeah, focus or agent. Yeah. So, and it's not exactly rewriting in the co-slice category because I don't need to have a map in from A into I or R. Yeah, so it's really just imposing a sort of way of declaring the constraint that you're related.
Sorry, Adam, can you please wait for a moment? Yeah. So indeed, now if you so the question is then of course how you would if you do sequences with this. I mean, so basically semantics is once you plug wires, you are still required to have the same. But basically,
so these wires are typed, so you can't just you need to explicitly switch your agent or your focus. So that's what the these other things are meant to help you do more fluidly, the query and the weaken boxes, because it's a type check error if you try to plug in one wire type into a rule that's not expecting that interface really.
Yes. So I mean, but the plugging is constructed like one would expect you basically, because I mean the wire itself is an entire category basically of all of the morphisms from the specified object. So basically you construct it in a way that you essentially always matching the same match between when you plug wires, right?
Yes, exactly.
In all possible ways, of course. But
so basically so the ports of the maybe another way for anything is that the ports of these boxes are typed with agents, and you can only connect ports with wires of that type too. And yeah, the semantics is that like as you move along a wire, the agent doesn't change. Like which particular match you're talking about does not change by moving from one end of a wire to the other.
Yeah.
But yeah,
That's
if you go through this merge vertices box, you're both on both sides. There's the same focus or agent shape of two dots, but you can see they're focused on different parts of the graph when you go through this box.
Sure. Yeah.
So you can only change which particular morphism from the agent shape by going through a box.
And sorry, one final quick question. So you mentioned later that you have this idea of semi-Markov procedures.
Yeah.
At least in the special case of Petronet, can you recover continuous time Markov chains or its simulations?
Yeah. So I think that's kind of like what this slide was meant to say, which was that we actually can bypass all of the rewriting stuff and get a performant implementation that is exactly how you would do
sorry, this is just mass action semantics. Yes, I mean the way the timer looks is precisely mass action semantics. But I was more asking about the sequence. I mean, when you try to get simulations, is this this tau leaping algorithm from Markov chain theory that you're showing? This decision procedure, how to make a timed sequence of events in a Markov chain?
Yeah, I'm not familiar with that. I'm not familiar with that procedure, but if it looks something like this, then where you sort of schedule events to happen in the future, but yeah, maybe an event gets invalidated because you consumed a resource and then you just skip it. So if that's the algorithm, then yeah, that's what this implements.
It vaguely rings a bell. Would be maybe nice to see.
Cool. Yeah, no,
but you didn't work off pre-existing concept. That is something you guys.
Oh no. We did. So yeah. So this is really the largest contribution of Sean Wu, who is very steeped in the literature of these Petronet transition systems. So it's more that I'm going to defer to him for where he came, but he's the one who actually implemented this. There's a new Julia package soon to be released called Competing Clocks that implements a lot of algorithms for doing these types of simulations. So there's not just one, but we're using this particular first to fire semantics. But yeah, I'm sure he is familiar with what you're talking about. I just happen to not be. Yeah.
Excellent. Thanks a lot for now. So maybe I leave the floor to others.
Thanks, Nick. Is there any other question or remarks from the audience? I don't see.
I think Adam had a question. I don't. Adam, do you want to ask in the chat, or because your connection seems to be a bit?
He asked generically one question for games. Is it for games?
Yeah, I think that was just confusion about what the game of life is. I think there is a official game of life that's like a board game. Maybe.
Adam, do you want to add something? You want to ask something, Adam? Okay. If not, I think Nick, we could close for the time being. Okay, sorry. No, somebody. So Ziad asks, thank you for the talk. What types of labels do you allow edges and vertices to have?
Yeah, that's a great question. So
probably attributes also.
Yeah, so this gets into the notion of an attributed C-set. So normally, for directed multigraphs, you're just looking at this E to V subpart of the schema. And in which case, if you're just talking about attributes on edges and vertices, well, you can simply draw in attribute types as well as attributes into this schema. So this can take the value of any Julia data type, and you could put as many attributes on your vertices or edges as you want, though importantly, there's lots of other expressive things you can do with the schema. I mean, the schema is playing a similar role to the type graph in the graph rewriting literature, but we're considering, functors out of this schema into set as opposed to maps into a type graph. So there is a sort of duality there. Oh, I think Adam's internet is back.
I don't know how to stop this annotation, sorry.
Yeah, maybe I'll, well, I was able to put him in a waiting room, but his
sorry, we have to
his mark. Oh,
sorry.
Great.
Yeah, very sorry for that.
That's just is excitement. So yeah, I don't know if Saeed, if that answered your question, that there's really no constraints on these attributes. And yeah, I had that one slide earlier. Oh yeah, so maybe this is time to just show a hidden slide of this how to use CatLab, where this is an example of a chemical reaction representation where we have a set of molecules which have associated bonds and atoms, and each atom has an atomic number, which is a natural number, and every molecule has a stoichiometry, which is a floating point number. And so we can talk about, the reaction which produces O2 from nothing, and start using that as a building block for other chemical reactions. So yeah, the language is very flexible. So yeah, so maybe this example works partially to answer your question.
Okay. Thank you. Are there any other questions? Okay, if not, as I was saying, Nick, maybe we could close the streaming and
Yes.
To close the meeting. If there is anybody watching on YouTube, it is still possible to join the Zoom meeting. Okay, yes, Adam, we can also continue the discussion with Adam after closing the streaming. Thank you very much, everybody, for attending the talk, and see you next time. I don't know exactly when is the next talk scheduled, but it is.
Thanks, Andrea. So we are in 2 weeks. Sorry, I don't know what is happening here. In 2 weeks' time, we hear from Uwe Volta and colleagues on some. Sorry, I have to. Who's drawing this actually? Very sorry.
Who else? Yeah, I just removed Adam.
Yeah. So we will have a talk in 2 weeks' time. So have a look at the GReTA webpage, and thanks again, Chris, for a very nice talk. We'll now close the live stream, as Andrea said, but stay in Zoom for a moment.